I'd like to introduce to you Oleg Ursu. He comes from the University of New Mexico, working for Tutor Opera. He's a chemist by training. In 2006, transitioned over to the cheminformatics dark side, and he's going to be giving us a talk on Screen3D.
I'll talk today about my experience with a new tool from ChemAxon, Screen3D, which is a flexible shape and match screening method. And this all started in March when Nora asked me to test and evaluate Screen3D, and I said, yes, of course. I've been running virtual 3D shape screens for a couple of years now, so I was interested in seeing how this new tool will work. And I went ahead and downloaded. I don't know if probably many of you already know about ChEMBL database from EBI. This is a database of medicinal chemistry papers, and I selected the around 12 targets with good coverage in medchem papers. And I only selected the active compounds for each of these target, which have less than 10 micromolar activity in terms of IC50, Ki, Kd, Km. And okay. All of these targets, I forgot to mention, all of these targets are human targets except for the viral targets, H1V virus. Okay, so the workflow which I followed was standardized. A lot of the problems in ChEMBLs are related to how the compounds are represented, or they can sometimes, most of the times they don't have the salts, but sometimes they do have weird parts in them. So I had to clean up using standardizer from ChemAxon. Generated 3D confirmation with molconvert using command line. And you can see out of almost 600,000, it failed for about 3,000, which is pretty good, considering the type of the molecules you have in ChEMBL. Really long and weird peptide-like compounds. Then I selected from each data set 1% of the molecules to be used as queries. And the rest of the molecules from each data set was used as targets, and I added 30,000 compounds on top of those as decoys from the database to make it more interesting. Then I just went and followed the user guide from Screen3D. I got from Miklos and Adrian, and prepared the binary files which are required to run the Screen3D itself, and then with the last command line I ran the Screen3D itself. This by default runs, my understanding, it runs shape with pharmacoform, and it doesn't run the match. You need to specify a different command line option to run the match method. These are the hit recall rates for the first of the 6 targets. And just to make sure I have a baseline to compare with, I also run extended connectivity fingerprint similarity search using the same queries and targets as for the Screen3D. So exactly the same scenario, except instead of using shape and pharmacophore search, I used ECFPs. And you can see in most of the cases, the blue line is the Screen3D and the red one is ECFP. In most of the cases, Screen3D outperforms ECFPs. And this is the second set of the targets. As you can see, for most of the targets, you can reach 90% recall ratio by when you reach 10% of the screened target and decoy compound set, except for the tyrosine phosphatase and Thymidylate synthase, where you, oops, doesn't show on the screen. Okay. You can see here you need to go further to reach 90%. And for the Thymidylate synthase, you actually cannot reach 90%. So my question was, why for these two targets I cannot reach the same enrichment ratio, same recall rates as for the other targets, 10 other targets. So my first I looked at the molecular diversity within each set of the target, compounds from each set of the target, and as you can see, this is a pairwise molecular Tanimoto similarity score on ECFPs. And you can see there is not much difference between, I don't know if you can see, but have a laser pointer. This is the tyrosine phosphatase, and this is Thymidylate synthase. And if you look at the other distributions of the Tanimoto score, there is almost no difference. So this is not the reason why they underperform. Screen3D underperforms for these two. Then another important parameter when you do flexible alignment is the number of rotatable bonds in the queries and the targets unidentified. So this was the next parameter I looked at, and you can see for tyrosine phosphatase, it's more than 50% have more than 8 rotatable bonds. So this could explain why you get lower enrichment ratios because you have to search a higher conformational space, and by default, Screen3D generates a limited number of conformers, and I used the default running options at command line in terms of generating the number of conformers. So this can explain why you cannot reach the same enrichment. But for Thymidylate synthase, the number of rotatable bonds is comparable to, it's about the number of compounds which have more than 8 rotatable bonds, it's about 30%, which is similar to the other targets. And this doesn't explain it why. And then I went and actually, because I selected just 1% of the compounds to be used as queries, and the Thymidylate synthase has 280 something, almost 300 compounds. If you look at the compounds selected to be as queries on the top row, they have 3 different scaffolds, but the whole set of Thymidylate synthase has more than 30 different scaffolds. So sampling, it's important. That's why you cannot reach enrichment, because you simply don't cover the query molecules are simply too different from some of the molecules in the target set. And my next question was, if ECFPs perform so well, why in so many cases, I mean, they perform pretty well in some particular cases, but in most of the cases they don't. So I looked at the molecules which are ranked top 100 by Screen3D, and looked they at the same time were ranked well below 100 by ECFPs. And as you can see, the main reason ECFPs rank them so low is because a small substituent or a small modification in a scaffold or a side chain introduces big changes in the environments which are constitute the bit vector in the fingerprint. And this leads to low Tanimoto values, and of course it will give you low scores. But using a 3D alignment method, you can avoid those kind of issues. So from this point of view, it makes sense to use Screen3D. So in conclusion, this is a pretty good new tool for 3D flexible alignment. I was really impressed by performance. For some of the data sets, the runtimes were about 4 hours. It has pretty good hit recall rates on the target sets I used. It integrates well with the other ChemAxon tools. You can start with standardizer, use MolConvert to generate 3D conformation, and visualize the results with Marvin View, so you don't really need any external tools to run through the whole process and analyze the results. So I think it can be useful, in my opinion. Thank you for your attention. If you have any questions, let me know.
Do we have any questions?